Hello everyone, I am Andrea Pugnana, and this work is called Deep Neural Network Benchmarks for Selective Classification, and is a joint work with Lorenzo Perini, Professor Jesse Davis, and Professor Salvatore Ruggeri. The usage of AI systems to support decision making is spread across different fields, including high-risk ones. In these settings, making incorrect predictions can be harmful. Hence, there is an increasing need for trustworthy AI systems. One way to mitigate the error proneness of machine learning model is to allow them to refrain from providing a prediction. In this way, another agent can take care of the final prediction and reduce costly mistakes. Or we can get more information on those instances for which the machine learning model abstains. This is exactly what happens when human doctors face difficulties in diagnosing a patient. Selective classification is one of the most popular frameworks for building machine learning models that can abstain. In this framework, the classifier is paired with a selection function that acts as a gating mechanism and determines whether the machine learning model provides the prediction or must abstain. The goal of selective classification is to navigate the trade-off between the proportion of examples for which a prediction is made, the so-called model's coverage, and the performance improvements on the selected examples. Such a trade-off arises from focusing only on those cases where the model has a small chance of making a misprediction. This can be formalized by minimizing the selected risk, subject to the constraint of achieving at least a target coverage C. However, despite the increasing number of selective classification approaches appearing in the literature, we lack insights into the merits of existing methods. This is because existing empirical evaluations in the literature suffer from several shortcomings. First, they always involve less than 10 datasets and primarily consider only image data. Second, only a handful of approaches, never more than 7, are compared. Third, most studies mainly focus on comparing approaches based on a single metric. In our work, we are the first to provide an extensive benchmark of existing methods. We analyze 44 datasets with both image and tabular data. We include both binary and multiclass classification tasks, considering 18 different selective classification baselines. Moreover, we evaluate existing methods according to 5 different criteria. First, we evaluate methods according to their predictive performance. Second, we analyze whether methods are able to achieve the target coverage. Third, we study whether the instances are rejected homogeneously across different classes. Fourth, we evaluate how it is possible to flip the learning task and maximize the coverage given a certain level of risk. Fifth, we check whether existing selective classifiers can abstain over instances that are out of distribution. Regarding the predictive performance, our experiments show that there is no clear winner when enlarging the set of data and the number of baselines. Concerning coverage violations, we do not see large coverage violations across all methods. When looking at imbalanced datasets, our results show that most methods tend to reject instances belonging to the minority class. Our experiments also show that it is always possible to switch from minimizing selective risk given a target coverage to maximizing coverage given a target risk, without noticing significant differences across selective classifiers. Finally, when looking at out-of-distribution examples, our experiments show that selective classifiers are not able to detect and abstain on these cases. To conclude, we provide the first large-scale benchmark for selective classifiers, highlighting current limitation of existing approaches. These shortcomings can be seen as a starting point for different future directions. For any further doubt, these are my contacts. Please do not hesitate to contact us. Thanks for watching.